So this is the third sort of description of how you can apply, Bernoulli's equation to various things. So one of the things that you can do, if you look on Blackboard, in course documents, you can find things like this, where hopefully it'll open up. This is a little loud. Sorry about that. This is the fountain, which actually is not true. It's not the highest fountain in the world, but it's the fountain in Lake Geneva in Switzerland. They have a fountain which sprays up water a significant distance, actually. And you can actually find the link down here. It is basically it will jets to an altitude of 140 meters. And so they pump 500 liters of water per second to an altitude of about 140 meters. And which means that it leaves the nozzle at a speed of about 200 kilometers per hour. You can also, and so again, this gives you a fairly good idea of what it looks like. And so it really sprays up, quite a distance. Now, the actual highest fountain actually is the Jeddah fountain in Jeddah, Saudi Arabia. And it's, and so you can, this is at night. This thing's almost twice as tall. It again sort of sprays up, huge amounts, into the air. It's lit at night. Just the one in Lake Geneva also is lit at night. Really quite a bit, kind of an attractive one. It actually goes 375 kilometers per hour, and it sprays up 260 meters up into the air. So it also is extremely tall. It's under a huge amount of pressure. And so the question is, when you have a fountain like that, exactly how do you actually sort of understand it? And if you looked at any particular fountain, generally speaking, it's got some, here it has a nozzle. Somewhere underneath it, basically what it has is a large pipe that has, a significant amount of pressure, really high pressure underneath this. And it narrows down so that you don't, as we'll talk about, in the next sort of sets of lectures, it has some velocity, of the water as it reaches the nozzle. But when it leaves the nozzle, it ends up going at an extremely high rate of speed. And so the question is, well, how do you actually understand it? And at some level, basically what you've got is that you have, Bernoulli's equation, which sort of specifies how these things change. And if you just look on one side of the nozzle versus on the other side of the nozzle, the idea is that once the water leaves the nozzle, now you're at atmospheric pressure, and so the pressure's dropped significantly. The height hasn't really changed, right? So these two terms should be equal to each other, right? And so the idea is that the pressure drops by a significant fraction, and so what that means is that the kinetic energy basically skyrockets once it gets out into this region. So, and it's Bernoulli's equation essentially that determines that. Now, the idea here is that this only works assuming that you don't have any dissipative forces. And as we'll talk about the next lecture, this never happens. In other words, the viscosity of liquid essentially only it always eats up energy. And the only way that you can make Bernoulli equations work is essentially where you have a really low velocity out here so that the pressure is really well defined on one side versus the other side, and then you can actually sort of approximate it. Now, the other thing is that this thing sprays up a huge amount up into the air and then suddenly turns around. At the top, this is just like projectile motion, and so the point is that the pressure doesn't change. But now, because the kinetic energy now is zero, because essentially it's like throwing a ball up in the air. We're basically zero at the top. Then, because the pressures are the same, then essentially what you're doing is you're converting kinetic energy into potential energy. And so the height that it goes up into the air is just determined by the initial kinetic energy, and assuming that the initial height is zero. And so both of these fountains work that way. So by going by how high it goes up into the air, you in principle could just calculate the velocity with which the droplets have to leave the nozzle. Okay, and then furthermore, if you knew the size of the nozzle and you knew roughly what was back here, assuming that the pipe is really huge, you could figure out what the pressure is that it has within the pipe itself, and which also has to be pretty significant. Okay. Now, the other thing that you can do, let's double check the time. Yeah, we're doing okay. Is something simple. You could talk about the Angel Falls, which is here. It's the world's largest waterfall. It's 1,000 meters high. Essentially, the water's in free fall for almost 900 meters. If you look at this actually, this is actually a base jumper. That's people that are jumping off the top of this cliff, and you can with a parachute. But the idea is the water is actually in free fall for all this 1,000 meters. One thing that you notice, of course, is that things separate when it's down to here. So clearly it's breaking up into droplets. And so the idea here is that you have essentially, some sort of cliff. You've got water that's sort of spraying out, and it falls. And so the idea is that at all points it's atmospheric pressure, so you don't have to worry about that. But it has some initial speed, and it's got some initial height, which is really huge in this case. And the idea is that's equal as far as you go down. It's still at atmospheric pressure. But as it falls, the velocity should just be increasing, going up and up and up as the potential energy decreases. So in other words, this decreases, and so the velocity, kinetic energy, has to increase. Now what you get from that is you have some huge volume of water. If the water was to be continuous, the only thing that it could do would be to have a really thick volume of water here, and it would have to thin out as it fell because it's going faster and faster. It would just be sort of razor thin as it falls down. That never happens. And so essentially what happens is as it goes faster and faster is that essentially it breaks up into droplets in order to make sure that the density of the water is always the same. And of course, this is an overestimation about what the kinetic energy is, okay, because this completely ignores any sort of dissipation. And so, of course, what you know is if you have a small water droplet, you're going to have, well, its weight, which is really driving it, but you're going to have air resistance as well. And so, more than likely, the water droplets reach some final terminal velocity as it goes down. So Bernoulli's equation, again, it only works basically when conservation of energy really works and you don't have any other dissipative forces. So, and again, as you go through there, this is pretty amazing. It's worth actually looking at for both of these, is that people actually can jump off of this thing with a parachute, which is, again, sort of a similar sort of thing. Look at the other video.
Welcome to Angel Falls. Hey, buddies. Check this out. How beautiful is this?
It's 1,000 meters.
Yeah, I'm slightly nervous. Perfectly said. Venezuela!
We've got to be a little bit crazy to do this. So he's actually jumped off this thing. So, pretty impressive. So, anyway, it's fun to watch. Anyway.